So I'm going to describe a few more tech ideas. This is part of a series. These are all my own inventions, and they're based on various scientific principles and research. They're all available on my Medium articles. I'm transferring them over to Substack as well. And each of them, if you apply globally, has a very large potential impact. So this one requires a little bit of backstory. It's easy to produce radio and microwave photons. Radio and microwave are photons. They're wiggling electromagnetic waves. You can just make a microwave by drilling a hole in metal. It's a microwave cavity. And it's easy to produce visible light and infrared light. Infrared in particular, you just heat something up and it's producing infrared. But between those two frequencies of light, there's something called the terahertz gap. And the terahertz spectrum is difficult to produce. In fact, it was nearly impossible for a very long time. It required some very expensive equipment and sophisticated babysitting. But researchers were still testing terahertz photons on various things for years and years and years. And I remember reading the research done by some chemists back in 2014. And the chemists were looking at different molecules. Every molecule has its own resonance frequency. It can vibrate at a certain frequency. The same way that any length of tube, if you take a pipe and cut it, it's going to make its own resonant note when you play it. It may not be in tune to your pentatonic scale or whatever, but it will create a sound. There is a resonance frequency for every length of pipe. There is a resonance frequency for every molecule. And the resonance frequency of molecules is in the terahertz domain. They resonate at terahertz frequencies. So these researchers were beaming terahertz frequencies at chemicals, molecules, that were tuned to the resonance of the molecule. And when you have a chemical reaction, you got, like, for example, two reactants, two chemicals that you want to react together. And they're only going to react if their final products are a lower energy state. Just like water flows downhill, they're only going to seek that reaction state if the final products are lower energy. But they don't just go there automatically, because there's usually an energy barrier. You have to add energy to the system to overcome the barrier, and then they fall down to the lower energy state. And that's a problem because it means it's hard to do chemistry. So in chemistry, they look for catalysts, which are infinitely reusable compounds that assist in those chemicals' reaction toward their lower energy state. So a catalyst lowers the energy barrier until it's just like a slip and slide. It just slides from the reactants to the products. Excuse me. So what these researchers found is that you can use terahertz frequency photons to catalyze chemical reactions. If you're playing the frequency of light that the chemical resonates with, then the chemical reaction will occur without the energy barrier. It just slides straight to the outputs, the products. And I saw that, and I realized that there are hundreds of thousands, if not millions, of applications. And there are a few in particular that are really, really valuable. And that was something I tried explaining to people, and they waved their hands because they didn't want to believe that shining a light on something could cause chemicals to react. They just didn't want to read science. And I also had to wait because we didn't have a way to make the terahertz frequencies easily, cheaply. We couldn't scale up production of terahertz frequencies. And then it was about 5 years ago, a different set of researchers found a way to make terahertz frequency light at a low cost. And it's called the Terahertz Diode. Same way in a light-emitting diode, an LED, operates. You're shocking it with electricity, and that vibrates the structure to emanate photons of light at a certain frequency. So the terahertz diodes, the way you manufacture them is you heat up glass, silicon dioxide, in a vacuum chamber. Basically suck out all the air, heat up the silicon to the point where it turns into a gas. You can do this with lightning. Electricity will heat things up as much as you need. So once you have this gas, then it's going to deposit on a cool surface. Once it touches the cool surface, it cools down, it starts accumulating as a layer. So you have a thin layer of silicon dioxide, and you want to sandwich it between two layers of magnesium oxide. And you can do this sandwich effect multiple times. So you have these very thin flakes of glass with pigment on either side. And when you shock that with electricity, it's going to emanate photons in the terahertz frequencies that match the cavity. The spacing, the thickness, determines the frequency. So different thicknesses of glass will produce different terahertz frequencies. And they mentioned that research, and then there's been trouble turning it into a product because there wasn't a pre-existing demand for terahertz frequencies, and it was hard to control. My innovation is to say, don't try to control it. Don't try to specialize and make exactly the frequency that you want. That's a waste of time. That's too much quality control babysitting. So instead, you just mass produce these flakes of glass, and after you've made them, after they're done baking and annealing, then you take each little piece of glass and you use an interferometer. You use multiple other interference frequencies to try and measure what the terahertz frequency is of that piece of glass. This piece of glass produces 2.4 terahertz. This other piece of glass produces 3.7 terahertz. Every time you've measured that piece of glass's frequency, you put it in a bucket with all the other pieces of glass that produce that frequency. So you now have all these buckets that produce all these different frequencies of terahertz. And you're just mass producing them as quickly as possible, minimal quality controls. You don't want to have to babysit and specialize. And now you can take those terahertz frequency buckets and you can test them on different molecules, different chemical reactions. So then if someone else comes along later, some pharmaceutical or plastic manufacturer or other material scientists, there's so many different branches of chemistry. Someone comes along later and says, I need something that does this. You already have buckets of every kind. You've already cornered the market. So that's the fastest way to scale production at the lowest cost per unit across the entire spectrum of applications. That's the best market strategy for adoption and development of Terahertz diodes. And the key applications that I identified many years ago, more than a decade ago, one of them involves agriculture and another one involves medicine. So for agriculture, when we look at the quantity of light from the sun that hits a plant, there's a limit to how much of that sunlight the plant can absorb. Quantum mechanically, there's a limit for each photon being absorbed of 25%. Only a quarter of the sun's photons could ever be absorbed. And then chemically within the chloroplast, because it has to have a chain reaction carrying an electron, it's even less. So the best plant absorption is about 11% of the sun's energy, which isn't a lot. And most of that energy is used just to keep the plant alive. For really tiny plants like algae, you can get up to 3% of the sun's light turning into growth. Just 3% for some of the fastest growing plants. For most plants, it's 1% of the sun's energy or less is actually turning into plant growth. So it's a very small yield. And if you look at where that's happening in the spectrum, the sun produces a whole range of colors. There are different frequencies of light, from the infrared to the ultraviolet. And plants' chemistry can only absorb in the red band and in the blue band. There's this whole green and yellow zone where plants reflect that light, and that's why leaves look green. It's because they're reflecting the green light back at you. So the absorption is in the red band and the blue band. And if you look at those absorption curves, that's because of the chemical limits of chloroplast. So if you can play a terahertz frequency, you're hitting the leaf with terahertz photons which resonate with the chlorophyll and the chain reaction within the plant, then you can broaden that absorption band. The parts that would only absorb a little bit of that energy at that frequency now absorb more. And so it looks a little bit bigger. And if you can broaden the absorption band of plants just to capture 4% more sunlight, then that's 5 times as much energy into plant growth, which means plants grow 5 times faster. And the amount of energy you're putting in as terahertz photons is very small compared to the amount of energy that gets absorbed by the plant from the sun. It's a catalyst. You're putting a little bit of energy in to make the chemistry happen easier, which allows a lot more sunlight to be absorbed. So you're spending a very tiny amount of energy to send a certain frequency at the plant's leaves, and the plants are able to absorb much more sunlight, and that surplus of energy means the plants grow much faster. And for farming, for agriculture, that means that more of the ground is covered in greenery in the crop cycle. You know, when you first plant a crop, most of the ground is bare. It takes a while for the plant to cover the ground. And then you can also fit more cycles of planting to harvest within a year. There's places where you would only have a few months, and that's not enough time to grow a whole nother crop. Now you can fit a whole nother cycle of crop growth in that annual budget of time. So you would get more than 5 times as much food from the same amount of land. 5 times the plant growth is more than 5 times as much food. And so that's worth a lot of money, but in particular it would end food scarcity. And it would also mean that we could grow enough food for everyone on much less farmland. Most of the farmland on Earth is low yield and low intensity. The best farmland is much more productive than the worst farmland. So if you can make plants grow 5 times faster and get more than 5 times as much food, then you can use less than 1/5 as much land for farming to produce the same quantity. And that would allow you to bring all those other pieces of land back to natural habitat. So that's a big benefit for us, eliminating food scarcity. It would reduce our dependence on pesticides and fertilizers. Farmland would have higher yields, and you'd have more natural environment. In particular, when we look at trees and their woody growth, the portion of sunlight that turns into actual tree is very small. It's usually less than 1/4 of 1% of the sun's energy. Very, very small amount of solar energy turns into actual cellulose. So if we play the frequencies that catalyze absorption of sunlight, and we play the frequencies that tilt the plant's metabolism towards cellulose, so they're not producing 5 times more fruit, they're putting 5 times as much energy into the tree growth. Well, that 1/4% plus 4 or 5% total solar capture means that trees would be able to grow 20 or more times faster. And if you can get a tree to grow 25 times faster, then in a single presidential cycle, you have a 100-year-old tree. And so that would allow us to regrow devastated forest land very quickly. And anywhere that we bring rain, and my last video right before this talks about how to convect humidity from the coastline to bring rain hundreds of miles inland. If we bring more rain, we can grow a lot more forests, and that rejuvenates the habitat. It also allows us to sustainably log for woody materials that we use as carbon capture. It'll capture a lot of carbon. So given the amount of land that is currently arid or desert that could become forest, which would be carbon capture, we wouldn't have to worry about carbon capture. That would supplement our entire demand for carbon capture. We don't need fancy cars. We don't need to do anything else. So the production of these terahertz diodes is minimal cost per carbon capture and minimal cost per food production compared to all those other methods. You can shout to your blue in the face telling farmers that they should be doing regenerative farming, permaculture, and they're going to tell you that they don't have the funding to switch over. They're already deep in debt. You can tell people that they should all switch to electric vehicles, and that's going to require scarce minerals from poor countries where people are being enslaved to mine it in destructive practices. Same for solar panels. So this is using glass, abundant material, cheaply, to quickly scale to carbon capture and food production. And so you have more land to give to native habitat. You can rejuvenate the forests. The other application space is medicine, because you could find the frequencies which trigger and stimulate cellular regeneration and the building of the lattice that heals tissue. And there's a thermodynamic limit to that, not just a metabolic limit, but actually the heat exhaust from metabolism. When you're doing a metabolic activity, especially healing, you're burning a lot of calories and it produces a lot of heat. So the limit would be when you're beaming so much terahertz frequency, you're beaming enough photons at a wound that the metabolic activity of the cells while they're healing would actually cook you. That would be the limit. You don't want to go past that, because then you're cooking yourself with your own metabolic activity. So if we cool down the surface of a wound, we can accelerate healing many, many times faster than normal. Wound closure could happen in as little as a few hours. That's the cellular limit. We can see bacterial growth rates and eukaryote growth rates. We know that cells can multiply and regrow that quickly. And if we have healing that quickly, just by beaming terahertz photons at a wound, that takes care of accident injuries and recovery from surgery, which are the main costs of those kinds of wounds and trauma. Especially surgery recovery, because surgery is kind of dangerous, but the recovery from surgery is where most of the issues happen. And just in the US, that's a $3 trillion industry per year, which is a discounted future return for the lifetime of that industry of about $24 trillion. So that's a big potential market. That's a lot bigger than the top tech stocks. And that's just one application of terahertz diodes.